GE Aerospace and Lockheed Martin just announced the successful testing of a new kind of air-breathing jet engine, capable of powering missiles to speeds well in excess of Mach 5 in a smaller, cheaper, lighter, and more efficient package than the most advanced scramjets in testing today. This new kind of engine, dubbed a rotating detonation ramjet, combines two different types of exotic jet propulsion technologies, including complex dual-mode ramjets and the technological wizardry of rotating detonation combustion engines. The result is an engine that could not only propel missiles into the hypersonic regime, or speeds above Mach 5, but could also offer a big increase in range for the same amount of fuel burned. And as groundbreaking as this new rotating detonation ramjet really could be for the missile business, it could have even greater implications a bit further down the line, as this combination of advanced propulsion technologies gets rolled into ongoing efforts to produce truly reusable hypersonic aircraft powered by turbine-based combined cycle engines. Yeah, that is correct. We're going to talk about mashing two kinds of exotic jet engine technologies together to make an even better engine, and then how we could mash that into two more kinds of exotic jet engine technologies to very literally change the world. So let's dive into Lockheed and GE's new rotating detonation ramjet and why we may be on the cusp of a veritable revolution in high-speed flight. I'm Alex Hollings, and this is Air Power. On Wednesday, Lockheed Martin and GE Aerospace announced the completion of what they called a series of engine tests demonstrating the viability of a liquid-fueled rotating detonation ramjet for use in hypersonic missiles. And I will be the first to admit that's a mouthful that represents a similarly complex marriage of propulsion technologies that for a lot of folks might seem impenetrable at best or nonsensical at worst. If you've never had a good reason to consider the types of jet engine technologies being employed by the airline you're flying or the fighter jets zooming by overhead, you might be inclined to think that most jets are basically the same, just built in different sizes for different power needs. But in reality, there are lots of different types of air-breathing jet engines, ranging from engines that are little more than mature versions of the original turbojets fielded in the late 1930s, to others that are so complex and highly specialized they've never even made it out of a laboratory setting. Now, some jet engine technologies can work from a dead stop and function well at low speeds, making it possible for aircraft to take off and land, while others can only function when already flying through the air at high speeds, relying on the immense pressure of that inflowing air to function at all. And in order to make this concept palatable, let's try to divide the jet engine technologies we discussed today into two different categories, and then we'll try to marry those categories together in the end. The first category will be deflagration engines, or engines that see fuel burn at subsonic speeds, and the second will be detonation engines, or engines that see fuel burn at supersonic speeds. And we'll start with deflagration engines because they're the ones most people are familiar with. Traditional turbofan and turbojet engines, like those found in today's aircraft and cruise missiles, use a fan at the front and a compressor to suck air in and compress it to be mixed with fuel and ignited, with that ensuing pressure flowing out the back as propulsion. The fans allow these engines to function even when the aircraft is at a dead stop, and they can continue to accelerate all the way up past Mach 2. But the efficiency of these engines really drops off dramatically as you try to approach Mach 3. Ramjets, on the other hand, have no compressors or really moving parts at all. Instead, they rely on the pressure of air flowing into the intake at high speed, along with shock waves produced through very intentional inlet design to provide compression. And as a result, these engines can't function at a dead stop at all. Ramjets often have an interior body mounted in the intake to force the airflow around, slowing that inflowing air to subsonic speeds to make it more manageable for ignition. At Right around Mach 3, the inflowing air pressure is sufficient for a ramjet to really come alive, and it can continue to accelerate all the way past Mach 5 and maybe even as high as Mach 6. At around that point, the subsonic airflow through the engine is just no longer sufficient to continue accelerating. Supersonic combustion ramjets, more commonly called scramjets, take the ramjet concept even further, removing that inner body completely and allowing the air to flow through the engine at supersonic speeds using shock waves created again through very intentional inlet design for compression. As a result, scramjets are capable of sustaining even higher speeds, likely eventually in excess of Mach 10 or maybe even Mach 12. The fastest scramjet test to date came in 2004 when NASA's scramjet-powered X-43A achieved Mach 9.6 at an altitude of around 110,000 feet. Now, in 2021 and 2022, Lockheed Martin partnered with Aerojet Rocketdyne to produce a scramjet engine for the Air Force's Hypersonic Attack Cruise Missile, or HACM, though despite its successful testing, a production contract was ultimately awarded to Northrop Grumman and Raytheon scramjet instead. And finally, we have a dual-mode ramjet, like the one that makes up half of the engineering in GE and Lockheed's new design. In simple terms, a dual-mode ramjet can function as either a ramjet or a higher-speed scramjet through the use of things like variable inlet geometry. In other words, moving control surfaces in the jet's air inlet can be used to create a series of shock waves, or a shock system, that slows inflowing air to subsonic speeds when the engine is functioning as a ramjet. As it continues to accelerate to higher velocities that better suit a scramjet, those moving control surfaces in the inlet shift to produce a different shock system that won't slow the inflowing air as much, allowing that same engine to then allow for supersonic airflow. So, in short, a dual-mode ramjet is just a ramjet and a scramjet in one. This is where Lockheed Martin's expertise probably came into play for this new engine with GE. Lockheed is no stranger to dual-mode ramjets, having successfully ground-tested a turbine-based combined-cycle engine for their now mysteriously vanished SR-72 program that, among other things, included a dual-mode ramjet back in 2017. Now, this experience and others all but certainly informed Lockheed's inlet design being used in this new joint engine with GE. Now, even though we all tend to use the word detonation to describe what happens to the air-fuel mixture inside any kind of internal combustion engine when you hit it with a spark, in reality, the mixture is actually burning through that process we talked about before called deflagration. Deflagration, once again, means the air-fuel mixture that's ignited burns away at high subsonic speeds. Now, even in scramjets with supersonic airflow, the ignited air-fuel mixture still burns subsonically through deflagration. And while these engines can be pretty darn efficient, deflagration is an inherently less efficient process than you'll find in our other category of jet engines, ones that leverage detonation instead. And just as we built from turbojets to scramjets to explain deflagration engines, we'll start with simpler detonation engines and work our way up to the rotating detonation technology employed by GE and Lockheed's new engine. Now, in a lot of ways, a rotating detonation engine is an extension of pulse detonation engines, or PDEs, which are in themselves an extension of pulse jets. Well, this lineage may seem confusing. Walking through each of them as developmental steps might make it easier to wrap our heads around RDEs, so just bear with me here. Pulse jet engines also use deflagration, just like those other jet engines we've discussed so far. But rather than a continuous ignition process, pulse jet engines work by mixing air and fuel within a combustion chamber and then igniting the mixture to fire out of a nozzle in rapid pulses for propulsion. And while these aren't detonation engines, they are the basis for the first detonations we'll talk about today, which are called pulse detonation engines. At a fundamental level, detonation is a lot like it sounds, an explosion. In contrast to deflagration and detonation, the air-fuel mixture burns a whole lot faster. Deflagration might burn at around 10 meters per second, whereas detonation can burn as fast as 2,000 meters per second. And to help make better sense of that, I'll quote my friend Dr. Chris Combs, a D. Howard endowed professor of hypersonic and aerospace engineering at the University of Texas, San Antonio. Quote, "You can get more efficiency by cramming all that reaction during a really short time in space. There's, at least from a thermodynamic standpoint, potential for much higher efficiencies in engines that burn through detonation rather than deflagration. When the air and fuel are mixed in a pulse detonation engine, they're ignited, creating deflagration like in any other combustion engine. But within the long exhaust tube leading out of that engine, a powerful pressure wave compresses any unburnt fuel ahead of that ignition, heating it above ignition temperature in what's known as the deflagration to detonation transition, or DDT. In other words, rather than burning through the fuel rapidly, the mixture explodes, producing more thrust from the same amount of fuel expended. In pulse detonation engines, or PDEs, the air-fuel mixture ignition still occurs in pulses, just like in a pulse jet, but the detonation method allows them to propel vehicles to much higher speeds, potentially believed to exceed Mach 4. And again, because detonation releases more energy than deflagration, detonation engines are generally more efficient. Now, in May of 2008, the Air Force Research Laboratory made history by building the world's first crewed pulse detonation-powered aircraft using a scaled composites home-built plane called the Long EZ. Now, this unusual-looking Frankenplane managed a speed higher than 120 miles per hour during its first test flight, with test pilot Pete Siebold at the stick, and they reached altitudes of between 60 and 100 feet. Not necessarily all that impressive, but more importantly, the Air Force Research Lab claimed the engine produced roughly 3 times more thrust than a standard jet engine would from the same amount of fuel burned. And then a rotating detonation engine takes that PDE concept to an even higher level. Rather than having the detonation wave travel out the back of the aircraft as propulsion, it instead travels around a circular channel within the engine's combustion chamber itself. Fuel and oxidizers are added to the channel through small holes, which are then struck and ignited by rapidly circling detonation waves. According to Dr. Combs, it isn't uncommon for a rotating detonation engine to have 3 or even 5 of these detonation waves circling the chamber at once. The result is an engine that produces continuous thrust rather than thrust impulses like a PDE, but that also provides the improved efficiency of detonation combustion rather than the deflagration that you'd find in conventional jet engines. This time, I'm going to quote legendary aviation journalist Steve Trimble from a conversation we had in 2022. Quote, "In theory, rotating detonation engines are a bit like the leap from turbojets to turbofans in the 1960s, but for high supersonic vehicles. It should give you a big jump in specific impulse or fuel efficiency, and if you can figure out how to package it in a way that doesn't make things significantly heavier or less aerodynamic, you should be able to get a nice range boost out of it." Now, the high supersonic speeds achievable with a rotating detonation engine, combined with their fuel efficiency, is the basis behind DARPA's Gambit missile program, which aims to field RDE-powered missiles that can fly further than today's weapons without needing larger airframes to carry more fuel. But rather than following suit, in 2023, GE Aerospace announced their ongoing efforts to marry the combustion process of a rotating detonation engine with the high speeds made possible by dual-mode ramjets. And the result is a new kind of propulsion system that can allow for subsonic or even supersonic airflow while using multiple continuous detonation waves to ignite and burn through that compressed air-fuel mixture in the process of detonation rather than deflagration, again, allowing for higher speeds and less fuel burned. I'll quote Mark Reddick, Vice President and General Manager of Edison Works Advanced Programs at GE Aerospace. Quote, GE Aerospace's hypersonic capabilities continue to advance at a rapid pace, and this collaboration with Lockheed Martin is another step forward in our journey. The testing on the rotating detonation ramjet and inlet exceeded expectations, and we're excited about this collaboration continuing to mature our advanced air-breathing hypersonic propulsion technologies. Now, because rotating detonation combustion produces more thrust for the same fuel burned, that means these new engines could allow for a number of big possibilities for future missiles. If you incorporated it into a weapon design that already exists, for instance, well, you could cover greater distances with the fuel already on board, or you could swap some fuel out for larger payloads without suffering a loss in range. Likewise, you could field smaller weapons that offer the same range and payload as today's weapons, allowing for an increase in weapons that you carry into the fight, and a whole lot more. So now let's briefly break down exactly how a missile using this new propulsion system might actually work. As advanced as a rotating detonation ramjet might be, it still won't be able to function from a stop or at low speeds. So, just like today's hypersonic cruise missiles in testing, this new missile will need to be launched under the power of a conventional rocket engine to gain the necessary speed and altitude for the ramjet to come online. Now, according to Lockheed Martin, their specifically designed inlet geometry, combined with GE's rotating detonation technology, allows their engine to achieve ignition at lower speeds than today's ram and scramjets can, which would in turn allow for the use of smaller and less expensive rocket boosters. Now, it isn't clear how low those speeds might actually be, but it is worth noting that back in 2013, Lockheed Martin's hypersonic program manager and the lead on the SR-72 program, Brad Leland, told USNI News that a focal point of their effort had been getting their dual-mode ramjet to function well at speeds well below Mach 3 in an attempt to bridge the velocity gap between efficiency velocities for turbofans that top out a bit over Mach 2 and scramjets that don't want to function below Mach 3. Once the missile is traveling at sufficient speed for that ramjet to come online, the rocket booster would detach and fall away. Now, Lockheed Martin's inlet would begin gobbling up the supersonic air flowing into it with a design carefully crafted to produce a sufficient shock system to create the necessary compression, while also slowing that airflow again to subsonic speeds. As the missile continued to accelerate up past Mach 3 and toward Mach 4, the shape of that inlet would shift to reduce the severity of the shock system and allow for higher speed air to flow through the engine until ultimately transitioning into full scramjet functionality that could, at least in theory, slingshot the missile to more than 7,000 miles per hour as it closes with its target. Inside that engine, GE's rotating detonation combustion technology would see multiple detonation waves circling the combustion chamber, igniting inflowing air and fuel in a much more efficient way than any jet engine in service in any aircraft or missile on the planet today. But if you've followed this channel for a while, you know that I've got mixed feelings about the long-term utility of hypersonic missiles, especially hypersonic cruise missiles. The hypersonic glide vehicles in service for Russia and China today are, to some extent, just an extension of ballistic missile technology, being carried aloft via a conventional rocket booster along a high-arcing ballistic flight path before separating from that booster at the apex of that flight path and gliding, unpowered but at extreme speeds and maneuvering down toward targets back on Earth. Hypersonic cruise missiles, on the other hand, work well, like any other cruise missile once their engines are firing, just at much higher speeds. And that means they fly along more horizontal flight paths, more like a fighter jet than a rocket, under the power of an exotic propulsion system like the rotating detonation ramjet Lockheed and GE are building today. Once they reach their target, the explosive payload on board, combined with the immense kinetic energy of a Mach 5 plus impact, destroys the target and the fancy propulsion system inside the missile. And when it comes to fancy and expensive propulsion systems, I would just much rather buy one or two that I can use over and over again in an aircraft than 100 that I can only use once in each missile. And that brings us to yet another smashing together of engine technologies and the turbine-based combined cycle propulsion systems being developed for reusable hypersonic aircraft. Now, we've already gone over how turbojets and turbofans work and how ramjets and scramjets work. So, in order to understand what a turbine-based combined cycle engine is, just stick those two together. In a turbine-based combined cycle, or TBCC engine, like the Chimera and Chimera II engines being built by Hermes, or the SR-72 propulsion system tested by Lockheed now nearly a decade ago, you take a turbojet or a turbofan engine capable of powering an aircraft from a stop up to speeds in excess of Mach 2, and then you just marry it to a ramjet or scramjet that can continue that acceleration up beyond Mach 3, 4, 5, and beyond. When it comes time to come back for a landing, you just decelerate back through those same steps in reverse, ultimately transitioning from scramjet to ramjet to turbofan power, as one example, as you slow down for a safe landing. Now, this concept has been demonstrated in bench tests and wind tunnels for years now, but to date, no firm has managed to cram all that engine into a single aircraft and then get it airborne, at least as far as we know. There is actually a fair bit of reason to suspect that it may have happened behind the classified veil by now. But nonetheless, one of the biggest reasons these engines haven't really taken off comes down to weight. A TBCC engine is, after all, really just two engines bolted together, one for low speeds and one for high, and that means that whenever one engine is functioning, the other is just dead weight. And when it comes to high-speed aircraft design, dead weight is never a good thing. And that is where the reduced size made possible by Lockheed and GE's new rotating detonation ramjet could have a huge impact on hypersonic aircraft development in the future. It could mean dramatically reducing both the internal volume and the weight of the ramjet half of that TBCC engine. Heck, on a long enough timeline, rotating detonation combustion could even find its way into advanced turbofan engines themselves, allowing for a rotating detonation TBCC engine that can propel an aircraft from a dead stop to Mach 10 and back again while still being small enough to be genuinely practical for both military and maybe even commercial applications. So, while this new rotating detonation dual-mode ramjet could be a very big deal for the next generation of high-speed missiles to come, the technology that comes from this effort could do a whole lot more than just deliver warheads to foreheads. We're talking about an aviation revolution unlike any since the inception of the turbojet nearly a century ago. And just to be clear, I'm not just talking hypothetically about using this technology for aircraft. About 4 months ago now, in September of 2025, GE Aerospace announced the successful demonstration of their rotating detonation ramjet in 2 different sizes. One meant for missile applications, and another, roughly 3 times larger, meant for aircraft. But, of course, before any of that can happen, this new Franken engine being built by Lockheed Martin and GE needs to get off the ground. And at least for now, it isn't clear exactly when we can expect that to happen. But you can rest assured that I will be keeping my ear to the ground for news about this one. And with that ends yet another edition of Air Power from Sandboxx News. I'm Alex Hollings. Make sure to swing by sandboxnews.com today and every day for all the latest in news, entertainment, and now merch from all around the force. If you got anything out of today's video, make sure to click like and subscribe down below, and make sure to leave me a comment so I know what I should cover next. And then, make sure to tap on the bell icon too, so you never miss a drop from Sandboxx News.